Coriolis force is a topic that we might have learned in school. It's abstract and imperceptible. However, Coriolis force always surrounds us and partially forms how the Earth rotates. And yes, so what is Coriolis force? In 1835, a French scientist published a paper considering supplementary and fictitious forces, one of which is Coriolis force. Now we have questions about Coriolis force. Where is it from? How is it formed? Are there any natural phenomena due to this? First thing first, we all know that the Earth rotates once every 24 hours. For people on Earth, we might think we are static, but we are just relatively static. Because we're always moving with the Earth at the speed of 1,037 miles per hour. To be explicit, the Earth rotates at the speed of 1,037 miles per hour at the equator. A point at the equator moves faster than one at the poles. For instance, if we were to go from the equator to about 30 degrees north latitude, the speed would considerably decrease from 1,037 to about 880 miles per hour. And why do we mention this? Here's the Coriolis force formula. M refers to the mass of air. Omega refers to angular velocity. Sin theta refers to latitude. And V refers to tangential velocity. And all these elements above multiplied by each other is F, which refers to Coriolis force. And we don't have to know how this formula was formed. There's one thing we know indeed. When latitude goes up, the force goes up. Which means the force at the equator is zero. And the magnitude of Coriolis force is also related to the speed of airflow. If airflow speed goes up, Coriolis force goes up. And here's the fact about Coriolis force. The paths that airflow takes are different in northern and southern hemispheres. The two red lines are the paths that airflow was supposed to take, whereas it takes the green line instead. The two green lines are also called deflection. Air, or objects moving from high pressure to low pressure in the southern hemisphere, goes clockwise and appears to deflect towards the left. On the contrary, everything will be opposite in the northern hemisphere. Here's another example. If you were to throw a ball in a straight line from the equator to your friend in North America, you'll find out the ball appears to be on the right side of your friend, because your friend is rotating with the Earth. During the process, the ball will maintain its rotation speed, but affected by Earth rotation inertia. That's how deflection works. Of course, if you were to throw a ball from the equator to the south, everything will be opposite. Lastly, let's take a look at the trails. There's even a starker goal on the container trains. When we kick a ball, we'll see the deflection at once. And now, we know the answer.